Let's talk about vaporization. Here we have an illustration of a beaker with some water molecules, little Mickey Mouse heads here. The molecules in liquid water are constantly moving. They're like swimming around, right? The water's swimming. They're just moving around, and the average kinetic energy that they have is related to the temperature of the water. So they're moving around. If you have a particle near the surface that has maybe higher than the average energy, it's one of the more energetic ones, and it's running towards the surface, it may have enough energy to break loose and just go into the gas state. Well, this one's coming down, but this one's going up. It goes into the gas state, and then it does what gases do. It'll go in a straight line till it runs into something, and if the beaker is open like this, those molecules are just going to go off into the atmosphere. Okay, have you guys ever heard of the game Red Rover? Yeah, they don't let kids play that anymore, do they? Because you could get hurt. So in case you're not familiar with it, Red Rover is a childhood playground game where you have two groups of kids across a grassy field from each other, and they hold hands, right? And so you've got these two lines of students, and then I don't know who decided, but some bossy kid says, Red Rover, send Sally right over, right? So Sally from the other team comes running across the grass at this line, and she's going to try to break through your hands. Yeah, it is funny. It's like, that seemed like normal when I was a kid. We actually played that, and then you think about it now, it's like, what a weird, brutal game. Where did that come from? I really need to look it up, because where's the Red Rover come from? Anyway, okay, so I envision the surface of the water as being like a Red Rover line, okay? And this is Sally coming right over, and Sally comes towards the surface. If Sally has enough energy, she can break through those molecules that are holding hands in the Red Rover line. So part of that is how big Sally is, and part of it is how fast she's moving, right? Because kinetic energy is 1/2 mass times velocity squared. So if she runs really fast, she's more likely to get through. If she's running really slowly, or if she's just walking, she's going to just bump up against your hands and not get through, right? So that's what these molecules are doing. They're just all jumbled around, but they're going in different directions, and some of them will head towards the surface. If they have high enough energy, they will escape. And this is where the quote for the chapter applies. It's a wild dance floor there at the molecular level. So you also think of this as being like a mosh pit. There's a whole bunch of people, okay? So vaporization is when we go from the liquid to the gas state. And the opposite of that, going from the gas state to a liquid, is called condensation. Now this morning on my bedroom windows, there was condensation, right? Because during the night, the window's cold, and the air in the house has some humidity in it because we breathe, like regular people. And so the humidity then condenses on the window, right? Condensation. And then you hope that it evaporates during the day. Any questions? So the average energy increases with temperature. Mentioned that already. So here we have the distribution of kinetic energy at a particular temperature, fraction of molecules with this amount of kinetic energy. So over here, this dashed line is the minimum amount of kinetic energy that the molecule needs in order to evaporate. So at a low temperature, there's this little bit here, and for those of you have taken calculus, that's the area under the curve, right? That's the integration right there. We're not going to calculate that. Those molecules have enough energy to escape. If you heat up the liquid, the average increases, but more importantly, the distribution broadens out, and now we've got a lot more particles that are able to escape. So it's the high energy molecules that can escape, because we talk about the average kinetic energy. Some of those molecules are moving really fast, some of them might be barely moving at all, some are in the middle, right? And so it's only the fastest ones that can escape. So higher temperatures, you're going to have vaporization more quickly. So this is why the clothes dryer heats your clothes, right? So you've got wet clothes and you want them to get dry. You put them in the dryer and it heats them, right? Because at a high temperature, the water evaporates faster. Another way to increase the rate of vaporization is to increase the surface area. So if you had like half a cup of water in a drinking glass sitting on the counter, and you took half a cup of water and you spilled it on the counter, and it just like went all over the place, which amount of water is going to like just disappear, evaporate more quickly? The one that's all spread out, right? Because in order for the things to escape, they have to get to the surface, right? So if you have a lot of surface area, there are more molecules that have an opportunity to escape. Whereas if you have a very small surface area, most of the molecules just are never going to even get close to the surface. So increasing surface area will also increase vaporization. Liquids with stronger intermolecular forces will evaporate more slowly. So something like acetone evaporates very quickly. There, it's all gone. Ooh, sorry about that. Thanks. Water evaporates. Can you think of a liquid that just doesn't seem to evaporate?
Mercury.
Mercury does evaporate. What about cooking oil? It's a liquid, right? Ever have problems with your cooking oil evaporating? No. Well, other things evaporate at room temperature. Even when you heat it up, it doesn't evaporate. Like if you heat a pot of water, you have a boiling pot of water, and you leave it, the water will be all gone after a while. If you heat oil and leave it, it's going to take like forever before the oil evaporates.
Or you'll have fire.
Or you'll have a fire. Well, you don't want to heat it past the smoking point of the oil. But why doesn't it evaporate? Well, oil molecules are really long, and they're like cooked spaghetti, and they get all tangled around each other, and so the intermolecular forces that hold them together are strong, and so they're just not going to evaporate. So we have two words, qualitative descriptions. We have volatile and non-volatile. So a volatile liquid will vaporize easily. A non-volatile liquid does not vaporize easily. So vegetable oil is non-volatile. Acetone is volatile. So if that beaker with the water evaporating was insulated, what would happen to the temperature of the water as it evaporates? Well, you can read the slide and it tells you the answer there. But the molecules that are leaving are the ones that have higher energy. So the high energy ones are leaving. What does that do to the average energy of the ones that are left?
Lowers.
It makes the average energy lower. What's the measure of average kinetic energy of something? Temperature. So as evaporation occurs, the liquid will cool. Here we're talking about the beaker being insulated, because the other thing that would happen as that water cools down, heat moves from warm temperature to colder temperature, right? And so the air around it is going to be transferring heat and kind of opposing that temperature change. But when you get sweaty and you get liquid on your skin, right? And a breeze comes and you're like, oh, that feels so good. It feels cool. Because it's the higher energy water molecules that are evaporating, and they're taking their energy with them, and they're leaving cooler water behind. That's how swamp coolers work too. So vaporization is an endothermic process. Sometimes identifying endo and exothermic can be a little bit tricky. Always ask yourself, well, what could I do to make that thing happen faster? So to make water evaporate faster, am I going to heat it up or cool it down? I'm going to heat it up, right? Like putting your clothes in the dryer. So that means putting energy into it makes it happen better. So it's endothermic. So the opposite, condensation, must be an exothermic process. And this is something that doesn't really seem to make sense. Water condensing from a gas into a liquid is releasing heat into the surroundings. Yep, it is. Don't hold your hand over a steaming pot of water because that steam has a lot of energy in it, and when it condenses on your skin, it can really burn you badly. This vaporization condensation business also helps to moderate climate. So these are some numbers I pulled off the internet a while ago. Average daily temperatures in July for a period of 1971 to 2000 for Fresno and for San Francisco. So Fresno, average high 96.6, sounds about right, low 66.1. A difference of 30 degrees in one day. San Francisco, high of 68, low of 54, difference of just under 14 degrees in one day. And San Francisco is not very far north of Fresno. It's not like it's up by the North Pole or something. Because, you go up into Canada, it's going to be cooler just because of is that longitude? I think it's longitudinal difference. That's not what's going on here. San Francisco is literally surrounded by water. It's got the ocean in the San Francisco Bay. And so that water will evaporate and condense. So it evaporates during the day, which keeps the water cool, it takes up energy, keeps the temperature of the air from heating up as fast. And then at night, the water condenses, releasing energy and keeping things from cooling down so fast. And so you have a very narrow temperature range. I lived near San Francisco for a couple of years, and it seemed like it was actually colder in the summer than it was in the winter. It's like really weird. And that's why people like to go to the coast who live here, because it's really hot. Why is it so hot? We live in a desert, right? We live in a desert. There's very little humidity in the air, and there's very little water around us, big bodies of water, to absorb and release heat. So there's always that like week or two in the summer where it doesn't cool down at night. Look at the humidity level. The humidity is higher than average at that time when it's not cooling off. So it's water's fault. Campaign against water. Okay, so if there's energy involved, then of course we want to measure it and quantify it. So this is called the heat of vaporization, or the enthalpy of vaporization. You can write a chemical equation representing water evaporating, water from the liquid going to water in the gas state. And the heat for that process is 40.7 kilojoules per mole. So vaporization is endothermic, and so the delta H is always positive. The definition of the heat of vaporization is the amount of heat needed to vaporize 1 mole at the normal boiling point. So for water, normal boiling point's 100 degrees. At that temperature, it's 40.7 kilojoules per mole. There's a slight temperature dependence. If you're evaporating water at room temperature, it takes a little bit more, 44 kilojoules per mole. The opposite, we just changed the sign. So condensation going from a gas to a liquid, it's the same number, just opposite in sign. So this is a great conversion factor between energy and moles of substance, either vaporizing or condensing. Let's do a problem. Calculate the amount of heat in kilojoules required to vaporize 2.58 kilograms of water at its boiling point. So this is called using the heat of vaporization in calculations. So guess what? We need the heat of vaporization of water. So I'm going to write that down before I forget. It's 40.7 kilojoules per mole. That's a conversion factor that we're going to need that they might not give you in a homework problem. You'll have to go look it up. You don't have to memorize that for an exam. So what numbers are they giving us here? Well, they're giving us 2.58 kilograms of water. And what are they asking us to find? Heat in kilojoules. This is a dimensional analysis problem. It strikes again. So we're going to start with kilograms. We'll start with kilograms, and we're going to try to get to kilojoules. And we have to figure out how to get from one side to the other. Well, the units on the heat of vaporization are a big clue, because this relates kilojoules to moles. And with a lot of these types of problems, if you really aren't sure what's in the middle, give moles a try. Moles are often in the middle of calculations. So if I had moles in here, I could use this value to convert from moles to kilojoules. What do I need to convert from kilograms to moles? Grams. Because I can calculate the molar mass, but that's in grams per mole instead of kilograms. So there's my path. I've got 3 arrows. So I'm going to start with 2.58 kilograms of water. 3 arrows means 3 conversion factors. These are the units in the numerator: kilogram, gram, mole, kilojoule. Kilogram, gram, mole, kilojoule. And then I put units in the denominator to cancel these out. So I take this unit and put it down here. This is your review of dimensional analysis. And I take this gram down here because I need those other units to cancel out. So I'm left with the unit I'm trying to find. You put the units in first. You make sure they're crossing out, canceling correctly. Then you stick the numbers in. I think one thing that messes people up is they try to get ahead of themselves and they try to stick numbers in there, and then all kinds of funky things happen, and the answer's wrong. So this guy is kilojoules and moles, so that's going to go over here. It's 40.7 kilojoules per mole, so it's 40.7 goes with a kilojoule, and if you feel like you need a number down there, it'd be a 1. This is the relationship between grams and moles, right? So we can calculate the mass of 1 mole of water by adding the masses of what's in the water. And this is not a review of that, so I'll just tell you that's 18.02. And then here, we need to convert from kilograms to grams. Now, we could do this like we've been doing it, where we just, instead of writing the K, we just write 10 times 10 to the third, and we go on our way. Sometimes you don't think of that, or it doesn't seem like it would work. This is doing it the original way I taught you, and this is going to work exactly the same way. We have 1 kilogram on the bottom, and on the top, we're going to write 1, and what kilo means, which is times 10 to the 3. And if you sometimes get those conversion factors wrong, I still am seeing people telling me that 1 milliliter is equal to 1,000 liters. A milliliter is a cubic centimeter, and 1,000 liters would be 500 bottles, 2-liter bottles of soda. Not the same, right? We converted it backwards. If that happens to you, just write it all out so that you get the answer correct. And I can grab a calculator. So now we do a little math. 2.58 times 1 EE3 divided by 18.02 times 40.7. So my calculator is showing me 5, 8, 2, 7, just all those numbers. Significant figures, remember those? Is how we decide how many of those we should keep. How many sig figs should our answer have? 3. This number has 3, that's exact. That one has 4, this one has 3. So I want to stop there in the tens place. If you're rounding tens, hundreds, thousands, you need to be careful so that you don't change the value of the number. So I can round this to 583 and then replace this, hold that place with a 0. But if you sometimes mess that up, put it in scientific notation. So 5 in the decimal point, 8, and that'll round to 3, times 10. And we're looking at how many places are we moving the decimal point. I'm not counting from the end. I'm counting from where the decimal point actually is. 1, 2, 3. 3 places. 5,000 is a big number. I like big paychecks. I feel positive about them. My exponent is positive. Any questions? We looked at evaporation in an open container. What if the container is not open? Here we have an Erlenmeyer flask with a rubber stopper. So what's going to happen? Well, we're going to have water evaporating, and that will depend on the temperature of the water. It will also depend on the surface area. In this situation, the temperature and the surface area are constant. You say, well, as it evaporates, it's going to get colder. Well, that temperature change is pretty small, and this is not insulated. And so heat from the surroundings are just going to come in, and this is pretty much going to stay at the same temperature. So we've got evaporation. That's happening at a particular rate. Initially, there's no condensation because there are no gas molecules here to condense. After evaporation happens for a while, now we've got some water molecules up here, and they are bouncing around until they hit something. So they're bouncing off the walls, and eventually they're going to crash into the surface of the water and get trapped. They're going to condense. So the rate of them condensing is going to depend on how many particles there are bouncing around. The more particles bouncing around, the more frequently one will get trapped, right? So initially, the rate of condensation is 0, and it slowly grows here. The length of that arrow is getting larger, and it's going to keep getting bigger as more and more water evaporates until the rate of evaporation and the rate of condensation are equal. So we've got water molecules going into the gas state and water molecules coming out of the gas state at the same rate. So the actual number of gas particles is going to remain constant. It's different gas molecules, but it's the same number of them. And we call that a dynamic equilibrium. It's an equilibrium because the concentration or the pressure there is going to stay the same. It's dynamic because the molecules are swapping places all the time. Any questions? So we can look at the rate of these processes as a function of time. Rate of evaporation is constant because that depends on surface area and temperature. Those are not changing. But the rate of condensation depends on the concentration or the pressure of that substance in the gas state. The more particles in the gas state, the higher the rate of condensation. So this is going to grow as evaporation occurs, and eventually these are going to meet and continue at the same rate. So that's a dynamic equilibrium, and vapor pressure is the pressure of a gas in dynamic equilibrium with its liquid. So we usually don't talk about like a molarity or concentration of gas. We talk about its pressure. That's how we measure concentration of gas. So the vapor pressure, let's go back to this one. The vapor pressure is directly related to the number of molecules in the gas state. If these particles are held very loosely, what happens to the rate of evaporation? Something with weak intermolecular forces is going to evaporate quickly, right? Something with strong intermolecular forces is going to evaporate slowly. So if we have fast evaporation, we're going to end up with more particles up there, a greater pressure. So here, this rate, if you have weak intermolecular forces, the rate might be up here. If you have strong intermolecular forces, it's going to be lower. So the strength of the intermolecular forces are going to affect the vapor pressure. Here's a system at equilibrium. I think that's pentane. So we have some gas particles and we have some liquid particles, and they're evaporating, condensing at the same rate. What if we mess with it? What if we pull the plunger up and increase the volume of the gas? Well, is that going to cause the rate of evaporation to change? No. But it gives the gas more space to bounce around in, and if you have the same number of particles, then fewer of them will collide. Or we can think of it this way: increasing the volume here causes the pressure to drop. So the pressure is lower, and so this process is going to continue until that pressure has been restored. So it doesn't matter what shape the container is, how big the gas part is compared to the liquid part, the vapor pressure is going to be the same for a given compound at a given temperature. Here, compressing it, we're going to increase the pressure of the gas, increasing its concentration. That'll cause condensation to happen faster. And so, again, it will adjust itself until it gets back to the same pressure. And this is known as Le Chatelier's principle, that a system at equilibrium will act to minimize the disturbance. So we've decreased the pressure, it's going to try to increase the pressure. It's going to go back to its original vapor pressure. Any questions? Okay, so what would happen to the vapor pressure of a substance if its surface area was increased, but the temperature remained constant? So we have two processes. We have evaporation and we have condensation. How does increasing the surface area affect evaporation? It goes up, right? You spread the water around, it's going to evaporate more quickly. That's why in public restroom with one of those hand dryers, you want to rub your hands around because you're maximizing the surface area of the water. They'll dry faster than if you just stand there. It also makes you feel like you're doing something. So it'll make the rate of evaporation go faster. How would increasing the surface area affect the rate of condensation? So you think about the gas molecules bouncing around. Now we're giving them a huge target. More of them are going to hit the surface, right? Because that's when they condense, is when they run into the surface. If we have a very small surface area, I'm going to try to draw a picture. So basically we'll take this container and tip it on its side. So here, the gas molecules are going to bounce around, but there's a smaller area where if they hit, they will condense. Here, when they bounce around, There's like surface area of water everywhere, and so they're going to condense more rapidly, right? So the increase in evaporation and the increase in condensation match each other. So what do you think the answer is? Stays the same. The vapor pressure is the same. It doesn't matter what shape the container is. If we increase the temperature, the vapor pressure will increase because more particles have enough energy to escape, right? So the rate of evaporation increases, and so we're going to get more molecules in the gas state. Vapor pressure is going to be bigger. And this is a graph showing that vapor pressure versus temperature. Here's water. As you heat water up, the vapor pressure increases. Diethyl ether, ethanol, ethylene glycol. That's what's in, that's the antifreeze. So you can have a small change in temperature resulting in a large change in vapor pressure. Boiling. The boiling point of a liquid is the temperature at which the liquid's vapor pressure equals the external pressure. So what's happening here we have a pot of water boiling, right? We're getting these big bubbles that form. What's in those bubbles? It's not air. It's water vapor or steam. Because what happens here is the temperature is high enough that even in the interior of the liquid, there's enough energy for them to make a gas. So you start to form a bubble, and then more of them come in because everybody's got enough energy to form a gas. That bubble then, of course, rises because it's less dense than less dense than water. It comes to the surface and it pops. And there went a bunch of your water molecules. So what's defined as the normal boiling point is the boiling point, the temperature at which its vapor pressure equals 1 atmosphere. So that would be 100 degrees for water. Let's go back to this one. So here's water. Water's vapor pressure is 760 or 1 atmosphere when it reaches a temperature of 100 degrees. For ethyl alcohol, its vapor pressure equals 1 atmosphere or 760 at 78.3 degrees Celsius. Because ethyl alcohol molecules are not as strongly attracted to each other as water molecules. So you're going to get this high vapor pressure at a lower temperature. And here's diethyl ether, even weaker intermolecular forces, so that will boil at 34.6. So interesting, what happens if we increase the external pressure? Let's say we take the external pressure up to here. What does that do to the boiling point? Increases it. So if we say, well, what about this pressure? That might be 7, no, that might be 900. We're going to increase the temperature at which the water boils. If we decrease the pressure, we can decrease the temperature at which water boils. So I don't remember a lot of stuff from high school because it was like a long, long time ago. But one thing I remember very vividly was in honors chemistry class. The teacher got this, it looked like a big Erlenmeyer flask, but it's got an arm on the side. It's a giant filter flask, a vacuum flask. And it had water in the bottom. And he hooked it up to a pump, and so he was evacuating all the air out of this. And so he's, lecturing or doing whatever he's doing, and this pump is just chugging, chug, 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 pulling a vacuum. And after a while, the water started to boil. It was just sitting on the counter. There was no hidden stove underneath or anything. it just started to boil. And then he made all of us come up and touch it with our hands. And of course, the first person is like, touch boiling water? That's not a good idea. She touched it. It was room temperature. Felt just like touching the bench top. Because if you lower the pressure enough, water will boil at room temperature. It's really kind of crazy. It was very memorable. So here we are heating water, and as we add heat, the temperature rises. That makes sense. When we get to the point at which it starts boiling, the temperature stops increasing. That's not what we would expect. Because here, that vaporization is happening so quickly, all the energy that's going in is leaving as those molecules evaporate. So the temperature of this water cannot increase above its boiling point at the same pressure until you get all of the water evaporated. Now you have a gas, and the gas will increase in temperature. So this has implications for cooking, right? So if you're wanting to cook some spaghetti and you just got the pot boiling, you just got the water to a boiling point, or you're like, well, I'm going to let it get hotter, I'm going to let it boil for 10 minutes before I put the spaghetti in because then it'll be hotter, it'll cook faster. No, it won't. Because as you continue to heat that water, it just stays at the same temperature. It stays at 100 degrees. It's kind of strange. How can you get water to boil at a higher temperature? Increase the pressure. So if we increase the pressure, well, I can't do it on that graph. I did it on the other graph. So if we lower the pressure, it boils at a lower temperature. If we increase the pressure, it boils at a higher temperature. So altitude will do this. Denver is the mile-high city. It's like 5,280 feet above sea level. Well, atmospheric pressure there is less than 1 atmosphere. Water boils at less than 100 degrees. When you're cooking anything with water in it, the water is going to affect how the temperature rises, right? If you're boiling something and it's at a lower temperature, even though it's boiling, it's still going to take longer. Baking a cake is going to take longer, and that's why they have high altitude directions on there, because there are people that live up there in Denver, and they bake cakes too. So, do you guys know what an Instant Pot is? Mm-hmm. So this is a fancy modern version of a pressure cooker. So an Instant Pot, it's electric, heats up the inside, but it has this lid with a valve that you can close. So as things boil, as steam is created, it can't escape. And so the temperature will get higher because the pressure's higher. So, this one. So if I increase the pressure, the water will boil at a higher temperature and my food will cook faster. The reason frying food is faster than boiling food is because you can heat oil to higher than 100 degrees Celsius. You can heat it much hotter, and so you throw the French fries in the oil and they cook very quickly. But it doesn't work that way with water. Any questions? This says use this figure to estimate the boiling point of water at an external pressure of 200 torr. So here's the vapor pressure. We want to find the temperature at which the vapor pressure is equal to atmospheric pressure, which here the external pressure is 200 torr. So at 200 torr, where does this cross the line for water? Well, about right there. And this is multiple choice, and they're not trying to see how straight of a line you can draw. Even if your line is really pretty crooked, you'll be able to choose the correct one out of this list. So what should it be? 66. So you can get the water to boil at 66 degrees at a pressure of 200 torr. Any questions? Those vapor pressure curves are not linear, right? They're curves. And it is an exponential function, and this is what the equation looks like. We're not going to do anything with that. But you can take this equation and rearrange it into a linear form. Really what they're doing is taking the logarithm of both sides. And get natural log of the vapor pressure is equal to negative heat of vaporization over R, the gas constant, times 1 over the temperature in kelvins, plus the natural log of this number called beta. That is in the form of Y equals mx plus b. So this is Y, this is m, and this is x. So if we graph the natural log of the vapor pressure versus 1 over the temperature, we'll get a straight line, and the slope will be equal to this. So here's an example. Here we have the natural log of pressure at graph versus 1 over the temperature, and here's the dots, and yes, indeed, they are following a linear trend there, and so you can get, using linear regression like we've done in lab, you can get the slope of the line. So the slope of the line is equal to that many Kelvin, and that is equal to negative delta H over R, and you do a little bit of algebra, and you find out that delta H is, why did they do that? 28.92 times 10 to the third, or 2.892 times 10 to the fourth joules per mole. This is not a problem that really can be done in lecture, but it's asking us to find the heat of vaporization of carbon tetrachloride. So what you would need to do is you need to take these temperatures and calculate the inverse. So 1 over the temperature and make a list of those. And for the vapor pressure, you need to take the natural logarithm of those numbers and make a list of those, and then graph those numbers to find the slope, and then you can find delta H. We can also use this equation if we don't have a whole bunch of data. We can look at it with just 2 points. Typically, this is done to figure out what the boiling point is at a given pressure, or find out what the vapor pressure is at a given temperature. So natural log of pressure 2 over pressure 1 is equal to that same slope thing times 1 over T2 minus 1 over T1. There could be an exam question that uses this equation, but the equation is on the useful information sheet. So that's not something you should clutter your brain up with. We're going to need it, so I'm just going to write it out here so we don't forget. So propane has a normal boiling point of negative 42 degrees Celsius and a heat of vaporization of 19.04 kilojoules per mole. What is the vapor pressure of propane at 25 degrees Celsius? So we have information about 1 point that allows us to calculate something about a second point. So there's a bunch of letters in here. So let's just write them all down. There's a P1 and a P2, and there's a T1 and a T2, and there's a delta H, VAP, and there's an R. Well, R is 8.314 joules per mole Kelvin. And you also don't need to memorize that number. How do you know you want to use that one instead of the 0.08206? Because the units on the 0.081 are liter atmospheres. And we've got joules in here. So if we're dealing with joules, we want to use this value. And that, again, will be given on the information sheet. So we've got a bunch of numbers up here. We've got this temperature and this and this. So let's identify what those things are. Well, this is our heat of vaporization, 19.04 kilojoules per mole. We've got two temperatures. One is temperature 1 and one is temperature 2, and we can choose what we call it. Now, we're going to be solving for a pressure, and I know from experience it's easier to solve for pressure 2 because it's in the numerator. So I want pressure 2 to be what I'm solving for, and I'm going to choose the others accordingly. So that's pressure 2. So then it's asking, what's the vapor pressure? What is pressure 2 at 25? So this must be the 25 degrees Celsius. So T1 is the other temperature. And what did they not tell us? They didn't tell us what the pressure was when it boils at minus 42. Not directly. It has a normal boiling point. What does that mean about the pressure? 1 atmosphere. Regular pressure. Normal pressure. So that tells me that pressure 1 is 1 atmosphere or 760 torr. And I know because I did this problem last night, well, and because the answer is right up there, that it wants the answer in torr. So I'm going to use torr. We can't use degrees Celsius. We need to change this to Kelvin. So let's see. 273.15 plus negative 42. So this is 231.15 Kelvin. And this one is 298.15 Kelvin. This is a very messy equation algebraically, and so this is not one that you should rearrange first. Stick the numbers in, do the calculations that you can, and then do some rearranging. Otherwise, it's so ugly. So the natural log of P2, P1 was 760 torr, is equal to the vapor pressure divided by R Do you see any issues with the units there? This is kilojoules, and that's joules. So we can do that little trick that we've been doing and say, well, this is times 10 to the third joules per mole, because that's what the K means, times 1 over T2, 298.15 Kelvin, minus 1 over 231.15 Kelvin. So there are no letters, no variables on the right side, so we can just calculate that. And we're not going to try to find common denominators or anything silly like that. Negative 19.04 times 10 to the 3 divided by 8.314 times, and here's where you need to use parentheses. Open the parentheses, and then I have 1 divided by 298.15 minus 1 divided by 231.15. Close the parentheses, press equal. So this is equal to 2.226,399. This would have 4 sig figs. I'm going to have logarithms involved, and so we definitely don't want to round off too much. But the natural log of P2 divided by 760 torr is equal to this number. Now we need to solve for P2. The natural logarithm is a function, it's not a number, so you can't divide by it. You have to undo the function, do the opposite of it, the antilog. So that is e to the x. The antilog of base 10 logarithms, the log one, is 10 to the x. So I'm going to do e to the x for both sides, and I'm going to get P2 over 760 torr is equal to e to the 2.226399. .266,438. Little weird with logarithms. I'm not going to test you on sig figs here. So then to get P2 by itself, I need to multiply both sides by 760. Let's do that in a different color. So times 760 times 760. So let's cancel out. I don't know why I put a decimal point there. Let's just start that over again. 7042.49. The unit is going to be torr because that was the unit on the other pressure. So if we round this to 3 sig figs, that's we get 7.04 times 10 to the 1, 2, 3 torr. Any questions? So we heated water in an open container. We looked at evaporation in a closed container. We looked at just evaporation at the same temperature in an open container. What if we have a sealed container and we add heat? Kind of like a pressure cooker, except the pressure cooker never gets this pressured. So here we have a gas and a liquid, and as we heat this up, the gas is going to become more dense and the liquid is going to become less dense, and that will continue, and at some point those two states will merge and they become a supercritical fluid. It's not a gas, it's not a liquid, it's kind of both at the same time. Supercritical fluid. This happens above the critical temperature, Tc. So different substances have different critical temperatures, but above that temperature, the liquid cannot exist above that critical temperature. It'll be a supercritical fluid. You just can't have the liquid. And there's a corresponding pressure there, which would be called the supercritical pressure. The supercritical fluids are very useful as solvents. So, caffeine is in coffee. There's lots of caffeine in coffee, and some people don't want the caffeine in their coffee. Well, how do you get the caffeine out without taking out all the other compounds that make it taste like coffee? You can't use water, right? Nobody's going to buy used coffee grounds. Nobody will do that. Supercritical CO2 is useful for this. The caffeine will dissolve in the supercritical CO2, but all these other compounds will not. And so you can wash out the caffeine. And then it doesn't leave any harmful residues. It's like, ooh, there was some unevaporated CO2 in my coffee. Big deal. You're breathing it, right? No big deal. Any questions?